Mesenchymal stem cells, abbreviated as MSCs, are isolated from a 6 to 8 week old Sprague-Dawley female rat and cultured in a 10 cm petri dish until they reach about 80% confluency. To enrich the MSCs, the cells are stained with biotin-conjugated primary antibodies, followed by streptavidin-conjugated magnetic beads. Labeled cells are then separated into two fractions, the negative fraction and the positive fraction, by magnetic activated cell sorting. Subsequently, flow cytometry analysis is used to confirm surface marker expression. Finally, cloning cylinders are used to obtain single colony-derived MSCs.
Hi, I'm Lin Xiaozhang from the laboratory of Christina Chen in the Department of Chemical Engineering and Material Science at Michigan State University. Today we will show you a procedure for isolation and enrichment of red mesenchymal stem cells, as well as obtaining single colony-derived cells. We use this procedure in our laboratory for studying the proliferation and the differentiation behaviors of red mesenchymal stem cells. So let's get started.
Mesenchymal stem cells, or MSCs, will be isolated from a 6 to 8 week old Sprague-Dawley female rat. To begin this procedure, cut off the femurs and tibias from the back limbs of the euthanized animal. Remove the skin and muscles. Put the dissected femurs and tibias in 70% isopropanol for a few seconds and then transfer them to 1x-DPBS. The following steps should be performed in a biosafety cabinet. First, transfer the femurs and tibias to a 10 cm dish containing DMEM. Then, while holding each bone with tweezers, cut open the two ends with scissors. Attach a 22-gauge needle to a 3 ml syringe and fill it with DMEM. Insert the needle into one opened end of the bone and flush the marrow into a 50 ml tube. Repeat 2 to 3 times for each bone. When all the marrow has been obtained, resuspend the cells. Then pass the cell suspension through a 70 micrometer cell strainer to remove bone debris and blood aggregates. Spin down the cells at 200 Gs at 4 degrees Celsius for 5 minutes. After removing the supernatant by aspiration, resuspend the cells in 25 ml of MSC medium. Seed 10 ml of cell suspension into each of two 10 cm culture dishes. Incubate the culture dishes in a 37 degrees Celsius 5% carbon dioxide incubator for 1 to 2 weeks. Once the previously isolated rat MSCs reach a confluency of about 80%, aspirate the medium and add 4 to 5 ml of trypsin EDTA to each dish. Return the dishes to the incubator and incubate for about 5 minutes to allow cell detachment. Add an equal amount of culture medium to inactivate the trypsin. Collect cell suspensions in a 15 ml tube and spin cells down at 200 Gs 4 degrees Celsius for 5 minutes. Now we will demonstrate the enrichment of MSCs by two surface markers, CD54 and CD90, using the BDI magnet, a cell separation magnet from BD Biosciences. Begin by resuspending the cell pellet in cell staining buffer at 20 million cells per milliliter. Next, add biotinylated CD54 antibody and biotinylated CD90 antibody to the cell suspension and mix gently. After incubation on ice for 15 minutes, wash the labeled cells with an excess volume of 1x BD IMAG buffer. Spin down the labeled cells at 200 Gs 4 degrees Celsius for 5 minutes. Prepare the BD IMAG streptavidin particles by vortexing thoroughly, and then add 40 microliters of particles for every 10 million cells. Mix the particles with the labeled cells thoroughly, and incubate the cells at 6 to 12 degrees Celsius for 30 minutes. During this incubation time, label a round bottom test tube for collecting the positive fraction. When the incubation is done, bring the labeling volume to 20 million cells per milliliter with 1x BD IMAG buffer. Transfer the labeled cells to the positive fraction collection tube. Place the positive fraction tube onto the BDI magnet and let it stay for 6 minutes. Then, with the positive fraction tube still on the BDI magnet, remove the supernatant with a glass Pasteur pipette. Next, remove the positive fraction tube from the BDI magnet and place it on ice. Add 1 milliliter of ice-cold 1x BDI mag buffer and resuspend the cells by gentle mixing. Place the tube back onto the BDI magnet and let it stay for 2 to 4 minutes. Remove the supernatant with a new glass Pasteur pipette. Repeat the washing as described previously one more time. Finally, remove the supernatant with a new glass Pasteur pipette and then remove the tube from the BDI magnet. Resuspend the cells in 1 milliliter of culture medium and transfer the cell suspension to a 50 milliliter tube containing 25 milliliters of medium. Seed one 75 cm squared flask for maintaining the cells, and a 10 cm dish for flow cytometry. To begin the procedure for separating single colony-derived MSCs, plate cells at about 50 to 100 cells per 10 cm dish and incubate in a 37 degrees Celsius and 5% carbon dioxide incubator for 1 to 2 weeks. During this 1 to 2 week period, examine well-isolated colonies with an inverted microscope. Once the colonies have reached a sufficient size of more than 100 cells in each colony, mark the colonies with a permanent marker at the bottom of the dish. When picking a colony to be marked, make sure there are no surrounding colonies nearby. Aspirate medium and wash the dish once with 1x DPBS. Using sterile forceps, pick up a sterile cloning cylinder and gently place it around the marked colony. Repeat this until every marked colony has a cloning cylinder placed over it. Add 100 microliters of trypsin EDTA to each cloning cylinder and return the dish to the incubator. After 5 minutes, check the cells under the microscope to see whether they are rounding up. When the cells have lifted up, add an equal amount of culture medium to inactivate the trypsin. Mix the cell suspension with a 200 microliter micropipetter and transfer the cell suspension to a 60 mm dish containing 3 milliliters of pre-warmed culture medium. Label the dishes and put them back into the incubator. After their isolation, plastic adherent MSCs should be visible the next day after plating. As the cells continue to proliferate, confluent cells should look like the cells shown in this phase contrast image, where the majority are spindle-like or star-like. Subculturing is appropriate when cells reach about 80%